Hello there, and welcome to my channel. My name is Matthew Gray. I'm pleased you discovered this place tonight, because we're about to drift through the quiet luminescence of the stars themselves. Wherever you are in the world right now, let this be your moment to let go. Let the day fade behind you, the tension dissolve, and your mind become as still and clear as the space between constellations. Tonight, we're traveling outward to the stars, those ancient lights that have guided travelers, inspired dreamers, and marked the passage of time since long before humans walked the earth. Stars are more patient, more generous, and more beautifully orchestrated than most of us ever pause to consider. From the smallest red dwarfs that will burn for trillions of years, to giant suns hundreds of times larger than our own, to the dying embers of white dwarfs cooling in the darkness, the stars follow rhythms that connect them all into a single, breathing system. What you're about to hear isn't a collection of random facts. It's a journey through the hidden architecture of stellar life, the quiet patterns that govern how stars are born, how they live, and how they return their substance to the cosmos. Every star you've ever seen began as a whisper of gas and dust. Every element in your body was forged in the heart of an ancient sun. The light touching your eyes from distant stars left those surfaces years, decades, sometimes centuries ago, carrying with it the story of worlds you'll never visit but are connected to nonetheless. Some of what you hear tonight may shift how you see the evening sky. Other discoveries might simply wash over you like the gentlest starlight, soft, distant, and quietly unforgettable. If this peaceful sense of wonder brings you calm or sparks your curiosity, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, settle back, get comfortable, take a deep breath, and let's begin this slow and soothing journey through the lives of stars. Stars begin their lives in the quietest possible way, as clouds of gas and dust drifting through space. These clouds, called molecular clouds, can be hundreds of light years across, containing enough material to form thousands or even millions of stars. They're mostly hydrogen, the simplest and most abundant element in the universe, mixed with traces of helium and tiny amounts of heavier elements. For millions of years, these clouds simply exist, floating through the galaxy, too diffuse and too warm for anything to happen. But occasionally, something disturbs them. A nearby supernova might send a shockwave rippling through the cloud, or the cloud might pass through the spiral arm of the galaxy, where densities are slightly higher. Whatever the trigger, a small region of the cloud begins to collapse under its own gravity. The collapse is gentle at first, almost imperceptible, but it's also inevitable. Once started, gravity pulls more gas inward, which increases the gravitational pull, which attracts even more gas. Over hundreds of thousands of years, the collapsing region grows denser and warmer, slowly transforming from a cold, dark cloud into something that will eventually shine. As the collapsing cloud grows denser, the material begins to spin. All clouds have at least a tiny amount of rotation to begin with, and as they contract, conservation of angular momentum causes them to spin faster, just like a figure skater pulling in their arms. The spinning material can't all fall directly to the center. Instead, it forms a flat disk around the growing central concentration, like pizza dough spun in the air. Most of the mass still ends up at the center, where temperatures and pressures climb steadily higher. but the disk remains, orbiting the forming star. Within this disk, the same process that's building the star can also build planets. Dust grains collide and stick together, gradually growing into larger clumps. Over millions of years, these clumps become planetesimals, then planets. The star and its planetary system form together, siblings born from the same cloud of gas and dust, their fates intertwined from the very beginning. When we look at a young star still surrounded by its disk, we're seeing the same process that gave birth to our own Sun and Earth 4.5 billion years ago. Young stars don't ignite fusion immediately. For a long time, perhaps a few million years for a Sun-like star, the collapsing core simply heats up through compression. The material falling inward converts gravitational potential energy into thermal energy, causing the temperature to rise. During this phase, the object glows dimly from this heat alone, but it's not yet a true star. Astronomers call these objects protostars. They're hidden from visible light by the dense cloud of dust surrounding them, but infrared telescopes can peer through the dust and see them glowing in the darkness. Eventually, when the core temperature reaches about 18 million degrees Fahrenheit, something remarkable happens. Hydrogen nuclei, which are just single protons, begin to fuse together to form helium. Each fusion reaction releases a tiny amount of energy, and with trillions upon trillions of reactions happening every second, the energy output becomes enormous. The star ignites, fusion begins, and a new sun is born. From that moment on, the star will shine steadily for billions of years, supported by the energy released from turning hydrogen into helium deep in its core. The energy released by fusion does more than just make the star shine. It creates an outward pressure that balances the inward pull of gravity. Without fusion, gravity would continue collapsing the star down to an incredibly dense point. But the heat and pressure from fusion reactions push outward, halting the collapse and establishing a stable equilibrium. The star reaches what astronomers call the main sequence, a long, stable phase where it burns hydrogen steadily. Our Sun has been on the main sequence for about 4.5 billion years and will remain there for another 5 billion or so. Larger stars burn hotter and faster, exhausting their fuel in mere millions of years. Smaller stars burn cooler and slower, some destined to shine for trillions of years, far longer than the current age of the universe. During all this time, the balance holds. Gravity pulls inward, fusion pushes outward, and the star remains stable. It's a delicate equilibrium, but also a robust one, maintained automatically by feedback mechanisms that adjust the fusion rate if anything starts to change. The light we see from a star doesn't come directly from the fusion reactions in the core. It takes an extraordinarily long time for energy to travel from the center of a star to its surface. Photons, the particles of light, are created by fusion deep in the core, but they can't travel straight outward. The star's interior is incredibly dense, packed with atomic nuclei and electrons. Each photon travels only a tiny distance, perhaps a fraction of an inch, before colliding with a particle and being absorbed. The particle then re-emits another photon in a random direction. That photon travels a short distance and gets absorbed again. This process repeats trillions of times as the photon essentially bounces its way outward through the star's interior. In the Sun, it takes roughly 100,000 to 1 million years for energy created in the core to reach the surface. By the time we see sunlight, the energy in those photons was created by fusion reactions that happened when our distant human ancestors were just beginning to evolve. The light we'll see from the sun tomorrow was created long before recorded history began. Once photons finally reach the star's surface, they're free to travel through space at light speed. The surface of a star, called the photosphere, is where the density drops low enough that light can escape into space rather than being immediately reabsorbed. From the photosphere, light radiates outward in all directions, spreading through space as an expanding sphere. The intensity drops with distance, following the inverse square law. Double the distance, and the light is spread over 4 times the area, so it appears 1/4 as bright. This is why distant stars appear dim, even though many of them are intrinsically much brighter than the sun. The nearest stars are still so far away that their light has been travelling for years before reaching our eyes. When you look at Alpha Centauri, the closest star system visible to the naked eye, you're seeing light that left those stars about 4 years ago. Look at Sirius, the brightest star in the night sky, and you're seeing it as it was about 9 years ago. Each star in the night sky shows you its past, a glimpse of how it looked when the light began its journey across the void. Different stars shine with different colours, and those colours tell us about their temperatures. Hot stars appear blue or white. Cooler stars appear orange or red. The relationship between colour and temperature is precise and well understood. Blue stars have surface temperatures of 50,000 degrees Fahrenheit or higher. White stars like our Sun are around 10,000 degrees. Orange stars are cooler, perhaps 7,000 degrees. Red stars can be as cool as 4,000 degrees, though cool is relative when even the coolest stars would instantly vaporize anything that came near them. The color comes from the spectrum of light the star emits, which depends on temperature. Hot objects emit more blue light. Cool objects emit more red light. By measuring a star's color accurately, astronomers can determine its surface temperature, and from that, estimate its size, mass, and age. Color is more than just appearance. It's a window into the star's fundamental properties, a signature written in light that reveals what the star is and what stage of life it's in. The stages of a star's life unfold with a patience that makes human timescales seem like the blink of an eye. After forming and joining the main sequence, a star burns hydrogen in its core for most of its life. A star like the Sun spends about 10 billion years on the main sequence. More massive stars, burning their fuel faster, might spend only 10 million years there. Less massive stars can remain on the main sequence for 100 billion years or more, far longer than the universe has existed so far. Eventually, though, the hydrogen in the core runs out. What happens next depends on the star's mass, but the general pattern is the same. Without fusion in the core to provide outward pressure, gravity begins to win. The core contracts, heating up as it does. The temperature rise can be enough to ignite a shell of hydrogen surrounding the now helium core. Energy from this shell burning pushes the star's outer layers outward, causing them to swell enormously. The star becomes a giant, much larger in radius than before, though cooler at the surface, giving it a reddish color. Our Sun will one day become such a red giant, swelling to perhaps 100 times its current radius. Red giants are remarkable objects. Despite their enormous size, they're actually less massive than they were on the main sequence because they've been losing mass through stellar winds, slow but steady streams of particles blown off the surface. The outer layers of a red giant are so loosely bound by gravity that they can easily escape into space. Over millions of years, the star sheds significant amounts of material, returning it to the interstellar medium, where it can eventually be incorporated into new stars and planets. Meanwhile, the core continues to contract and heat up. In stars with enough mass, the temperature eventually becomes high enough to ignite helium fusion. Helium nuclei fuse together to form carbon and oxygen, releasing energy and halting the core's collapse once again. The star settles into a new equilibrium, burning helium in its core and hydrogen in a surrounding shell. This phase is shorter than the main sequence, lasting perhaps 100 million years for a sun-like star. Everything about stellar evolution happens slowly, measured in spans of time almost incomprehensible to creatures who live for mere decades. When helium in the core is exhausted, stars face a choice point determined entirely by mass. Stars like the Sun, with relatively modest masses, can't get hot enough to fuse elements heavier than carbon and oxygen. Without fusion to support them, their cores contract one final time. But electron pressure, a quantum mechanical effect, prevents further collapse. The core becomes a white dwarf, incredibly dense, packing roughly the mass of the Sun into an object about the size of Earth. A teaspoon of white dwarf material would weigh several tons. The outer layers, no longer held by the core's gravity, drift away into space as a planetary nebula, a beautiful, expanding shell of glowing gas. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers thought they looked planet-like through small telescopes, and the name stuck. The white dwarf at the center slowly cools over trillions of years, gradually fading from white to yellow to red to black, though the universe isn't old enough yet for any white dwarf to have cooled completely to darkness. More massive stars have more dramatic endings. When they exhaust helium, their cores are hot and dense enough to fuse carbon. Carbon fusion produces neon and magnesium. Neon fusion produces oxygen. Oxygen fusion produces silicon. Silicon fusion produces iron. Each stage happens faster than the last and releases less energy. Carbon burning might last 1,000 years. Silicon burning lasts only a few days. Iron is where the process stops. Fusing iron doesn't release energy, it absorbs energy. When the core fills with iron, there's no more fusion possible. The core, now with a mass comparable to the Sun, but compressed into a volume the size of a city, can no longer support itself. In less than a second, it collapses. Electrons and protons are crushed together, forming neutrons. The collapse halts when the entire core becomes a neutron star. A ball of neutrons, about 12 miles across, but containing more mass than the Sun. The sudden halt of the collapse sends a shockwave rebounding outward through the star. The shock tears through the outer layers, heating them to billions of degrees and blasting them into space. The star explodes as a supernova, briefly outshining an entire galaxy. Supernovae are the universe's alchemists. The explosion forges elements that normal stellar fusion can't create. Iron, nickel, zinc, copper, silver, gold, lead, uranium, every element heavier than iron in the periodic table, owes its existence to supernovae. These elements are created in the extreme conditions of the explosion and then scattered into space. Over time, they mix with the interstellar gas, enriching it. When new stars form from this enriched gas, they'll have more heavy elements than previous generations. Planets forming around those stars will be made partly from supernova debris. Earth's iron core, the gold in jewelry, the uranium in nuclear reactors, all of it came from supernova that exploded billions of years ago, before the Sun and Earth formed. We're built from the ashes of dead stars, our bodies containing atoms forged in the most violent events the universe produces. There's something profound in that, a connection between human existence and cosmic cycles that operated long before Earth existed and will continue long after it's gone. After the supernova fades, what remains depends on the original star's mass. If the core that collapsed was between about 1.5 and 3 times the Sun's mass, it becomes a neutron star. Neutron stars are extraordinary objects. Despite containing more mass than the Sun, they're only about 12 miles in diameter. That makes them incredibly dense. A sugar cube-sized piece of neutron star material would weigh about 100 million tons. The surface gravity is about 100 billion times stronger than Earth's. A neutron star's magnetic field can be trillions of times stronger than Earth's strongest magnetic fields. Some neutron stars spin hundreds of times per second, maintained by conservation of angular momentum as the star's core collapsed from something much larger to something tiny. These rapidly spinning neutron stars often emit beams of radiation from their magnetic poles. If one of those beams sweeps past Earth as the neutron star rotates, we detect regular pulses of radio waves, sometimes with extraordinary precision. These pulsars, as they're called, make excellent cosmic clocks, their pulses arriving with a regularity rivaling the best atomic clocks. If the collapsing core is more massive than about 3 times the Sun's mass, even neutron pressure can't halt the collapse. Nothing can. The core continues collapsing until it forms a black hole, a region of space-time where gravity is so strong that not even light can escape. Black holes have earned fearsome reputations, but they're actually just extremely dense objects with very strong gravity near them. Far away from a black hole, its gravity is no different than that of any other object with the same mass. If the Sun suddenly became a black hole, Earth would continue orbiting exactly as it does now. The Sun's mass wouldn't change, so its gravitational influence on Earth wouldn't change either. Only close to a black hole, within a few times its radius, does the gravity become extreme enough to trap light. The boundary where light can't escape is called the event horizon. Outside the event horizon, you could orbit a black hole safely, though getting too close would certainly be dangerous. Inside, escape is impossible, not because of some mysterious force, but simply because all paths through space-time lead inward. Black holes aren't completely black. In the 1970s, physicist Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation. This Hawking radiation is incredibly faint, far too weak to detect from any known black hole. But theoretically, it means black holes slowly evaporate over time. A black hole with a mass of the Sun would take about 10 to the 67th years to evaporate completely, a time span so vast it makes the current age of the universe seem like an instant. More massive black holes take even longer, but eventually, given enough time, even black holes fade away, their mass slowly converted to radiation and returned to the universe. Nothing lasts forever, not even the densest objects that physics allows. The universe operates on timescales that dwarf human comprehension, where billions of years are brief moments and black holes evaporating is simply part of the natural order. Patient processes working themselves out over spans of time too vast to imagine. Most stars aren't alone. About half of all stars exist in binary systems or multiple star systems, orbiting one another through mutual gravitational attraction. Some binaries orbit so close together that they nearly touch, their outer layers sometimes even merging. Others orbit at such great distances that you might not realize they're part of a system at all, separated by thousands of times the distance from Earth to the Sun. Binary stars form together from the same collapsing cloud, or sometimes two stars passing close in a dense stellar cluster can capture each other gravitationally. Once bound together, they orbit their common center of mass, following the same gravitational laws that govern planets orbiting stars. Close binary systems can interact in fascinating ways. If one star evolves into a red giant, its outer layers might overflow onto its companion, transferring mass. If one becomes a white dwarf or neutron star, it can pull material from a normal companion, creating dramatic outbursts as the accreted material heats up. Some of the brightest explosions in the universe come from binary stars interacting in these ways. Even when stars aren't in binary systems, they rarely form alone. Star formation typically happens in clusters where dozens, hundreds, or even thousands of stars form from the same molecular cloud at roughly the same time. Young clusters are beautiful objects containing many hot, bright blue stars that illuminate the surrounding gas with ultraviolet light, causing it to glow. The Pleiades, visible to the naked eye as a small grouping of stars, is a young cluster only about 100 million years old. It contains several hundred stars still surrounded by wisps of the dusty cloud from which they formed. Over time, clusters gradually disperse. Their stars drift apart as they orbit the galaxy, perturbed by gravitational interactions with other stars and gas clouds. Within a few 100 million years, most clusters dissolve completely, their member stars scattered throughout the galaxy. Our Sun almost certainly formed in a cluster 4.5 billion years ago, but its siblings have long since scattered. They're out there somewhere, stars that formed from the same cloud as the Sun, now spread across vast distances with no way to identify which ones they are. The Sun itself is a remarkably average star, neither especially large nor small, hot nor cool, bright nor dim. It sits comfortably in the middle of the stellar population, a yellow dwarf following a predictable path through its 10 billion year main sequence lifetime. Its ordinariness is actually reassuring. Special circumstances aren't required for planets to form or for life to emerge. Ordinary stars like the Sun, which make up a significant fraction of all stars, provide stable environments for billions of years. Red dwarf stars, smaller and cooler than the Sun, are even more common. They make up about 3/4 of all stars in the galaxy. These small stars burn their fuel so slowly that they'll shine for trillions of years. The universe isn't old enough yet for any red dwarf to have exhausted its hydrogen and moved off the main sequence. Every red dwarf that's ever formed is still shining, and all of them will continue shining for far longer than the universe has existed so far. They're the ultimate long-term residents of the galaxy, patient and enduring, outlasting nearly everything else. Red dwarfs have another interesting property. Because they're fully convective, meaning their interiors are constantly mixing, they can fuse all of their hydrogen, not just the hydrogen in the core. More massive stars like the Sun have a radiative zone where energy moves outward through radiation rather than convection, and this prevents complete mixing. The Sun will only fuse about 10% of its total hydrogen before the core runs out, and it evolves off the main sequence. Red dwarfs can fuse nearly all their hydrogen, making them incredibly efficient. When they finally do exhaust their fuel trillions of years from now, they'll contract directly into white dwarfs without going through a red giant phase. The universe will be unimaginably different then. Galaxies will have merged or dispersed. Most sun-like stars will have become white dwarfs or neutron stars. Even the cosmic microwave background will have cooled to near absolute zero. Red dwarfs will be among the last lights shining, slowly fading beacons in a dark and cold cosmos. The brightness of stars varies enormously. The most luminous stars shine millions of times brighter than the Sun. The faintest known stars emit less than 1/10,000th the Sun's light. This enormous range comes from differences in mass and temperature. More massive stars are hotter, and temperature has a strong effect on luminosity. A star twice as massive as the Sun might be 10 times more luminous. A star 10 times more massive could be 10,000 times more luminous. The relationship is steep. Massive stars burn incredibly bright, which is part of why they exhaust their fuel so quickly. They're spending energy profligately, shining brilliantly but briefly. Small stars are economical, sipping their fuel slowly, shining dimly but steadily for trillions of years. In the long term, the meek really do inherit the galaxy. The bright, massive stars blaze out quickly, while the dim red dwarfs persist essentially forever. Which type is better? Neither. They're different strategies, each successful in its own way, each playing a role in the galaxy's ecosystem. Stars also vary in their sizes, and size correlates roughly with other properties, but not perfectly. The Sun's diameter is about 864,000 miles. Red supergiants, like Betelgeuse, can be more than 1,000 times larger in diameter, big enough that if one replaced the Sun, its surface would extend past the orbit of Mars. If you could see such a star up close, it would fill your entire field of view, a vast glowing surface extending to the horizon in all directions. Yet despite its enormous size, Betelgeuse has only about 15 to 20 times the Sun's mass. Its density is incredibly low, more like a thin gas than what we normally think of as solid matter. At the other extreme, white dwarfs pack roughly the Sun's mass into an object the size of Earth, and neutron stars compress even more mass into a sphere 12 miles across. The range of densities in stellar objects spans tens of orders of magnitude, from tenuous giants to incredibly compact remnants. Temperature inside stars reaches levels difficult to comprehend. The Sun's core temperature is about 27 million degrees Fahrenheit. More massive stars have even hotter cores, sometimes exceeding 100 million degrees or more. At these temperatures, atoms don't exist as we normally know them. Electrons are stripped away, leaving bare nuclei surrounded by a sea of free electrons. This plasma is governed by electromagnetic forces and nuclear forces, with matter behaving in ways far removed from everyday experience. Yet even in these extreme conditions, the physics is well understood. Equations developed from studies of relatively cool atoms and molecules apply equally well to the ultra-hot plasma in stellar cores. The same quantum mechanics that describes electrons in room temperature atoms describes the fusion reactions creating energy in stars. The same thermodynamics that governs steam engines describes the flow of energy through a star's interior. Physical laws are universal, operating equally well in the most extreme environments as in the most mundane. Understanding stellar physics required centuries of observation and theory. Ancient astronomers knew that stars appeared to be fixed relative to each other, unlike planets which wandered across the sky. They catalogued star positions and brightnesses, creating maps of the heavens. Not until the telescope was invented in the 1600s did anyone realize that the Milky Way's cloudy band contained countless individual stars. In the 1800s, spectroscopy revealed that starlight could be split into spectra showing absorption lines, which indicated the presence of specific chemical elements. Different stars had different spectra, leading to a classification scheme that grouped stars by their spectral features. In the early 1900s, astronomers realized that this classification actually represented a temperature sequence, and that temperature correlated with other stellar properties. The Hertzsprung-Russell diagram, which plots stars' luminosities against their temperatures, revealed that most stars fell along a diagonal band called the main sequence, while giants and white dwarfs occupied different regions. This diagram became a cornerstone of understanding stellar evolution. Evolution of our understanding continues today. Modern telescopes can observe stars in unprecedented detail, measuring their oscillations, mapping their surfaces, detecting planets orbiting them, and analyzing the light from their atmospheres. Space-based observatories avoid atmospheric distortion, capturing sharp images of stellar nurseries and dying stars. Computer simulations model stellar interiors, calculating how energy flows from core to surface and how fusion reactions proceed under different conditions. These simulations match observations remarkably well, confirming our theoretical understanding. We can now create detailed models of how a star of any given mass will evolve, predicting when it will leave the main sequence, how large it will become as a giant, and what kind of remnant it will leave behind. The models aren't perfect. Some details remain uncertain, particularly around the complex interactions in binary systems and the exact mechanisms of supernova explosions. But the broad picture is solid, tested against countless observations, and found reliable. Reliable models allow us to determine the ages of stars with reasonable accuracy. We can't directly observe a single star evolving because stellar lifetimes are far too long. But we can observe many stars at different stages of life and piece together the sequence. Star clusters are particularly useful for this. All stars in a cluster formed at about the same time from the same molecular cloud, so they all have the same age. But they have different masses, and mass determines how fast a star evolves. Massive stars evolve quickly, so in a young cluster, the most massive stars have already left the main sequence, while smaller stars remain. By looking at which stars are still on the main sequence and which have evolved into giants, astronomers can estimate the cluster's age. The Pleiades, with many hot blue stars still on the main sequence, is young, only about 100 million years old. Globular clusters with no blue stars remaining and many red giants visible are ancient, often more than 10 billion years old, nearly as old as the universe itself. Ancient globular clusters orbit in the halos of galaxies, spherical distributions of stars surrounding the flat galactic disks. The Milky Way has about 150 known globular clusters, each containing hundreds of thousands to millions of stars, packed into a relatively small volume. Within a globular cluster, stars are much closer together than in the solar neighborhood. The nearest star to the Sun is about 4 light-years away. In a globular cluster core, stars might be separated by only a few light weeks, making close encounters between stars much more common. These encounters can disrupt binary star systems, exchange members between binaries, or even cause collisions, though actual stellar collisions remain rare even in the densest clusters. Globular clusters are also chemically distinct from stars in the galactic disk. They contain far fewer heavy elements, having formed early in the galaxy's history before supernova explosions had enriched the interstellar medium with carbon, oxygen, iron, and other elements. Their stars are old, their dynamics complex, and their continued existence a reminder of the galaxy's youth billions of years ago. Galaxies themselves are held together by the combined gravity of their stars, gas, and dark matter. The Milky Way contains 200 to 400 billion stars, though the exact number is uncertain. These stars orbit the galactic center in complex patterns, with stars in the disk following roughly circular orbits, while halo stars follow more elongated paths that carry them far above and below the disk. The orbital period depends on distance from the center. The Sun, located about 26,000 light-years from the galactic center, takes about 225 to 250 million years to complete one orbit. Stars closer to the center orbit faster, while those farther out orbit more slowly. The rotation isn't like a rigid disk, though. Different parts of the galaxy rotate at different rates, creating spiral arms and other structures. Despite this differential rotation, the galaxy maintains its overall shape, a balance between gravity pulling inward and the angular momentum of orbiting stars preventing complete collapse. Spiral arms are particularly interesting features. They're not fixed structures where the same stars remain. Instead, they're density waves, regions where stars and gas clouds are temporarily compressed. Think of traffic on a highway slowing down in a construction zone. Individual cars pass through the zone and speed up again, but the zone itself remains stationary. Similarly, stars and gas clouds pass through spiral arms, temporarily bunching together, then moving on. The arms appear bright because star formation happens preferentially in them. When gas clouds enter a spiral arm, they're compressed, which can trigger collapse and star formation. The resulting young, hot, blue stars are intrinsically very bright, so they light up the spiral arms prominently. By the time these stars age and dim, they've moved away from the spiral arm. The arm itself persists because new stars are constantly forming within it as fresh material enters. It's a self-sustaining pattern, maintained by the gravitational interactions of billions of stars and the inflow of gas from the galaxy's outer regions. Gas in galaxies provides the raw materials for new star formation. About 10 to 15% of the Milky Way's mass is in the form of gas, mostly hydrogen with some helium and traces of heavier elements. This gas exists in several forms. Cold molecular clouds, dense and dark, are where stars form. Warmer atomic hydrogen fills much of the galactic disk. Hot ionized gas, heated by supernova and stellar winds, occupies the halo. Gas constantly cycles between these phases. Cold clouds collapse to form stars. Massive stars explode as supernovae, blowing hot gas into the surrounding space. That hot gas eventually cools, condenses, and joins the cold cloud population again. The cycle takes tens to hundreds of millions of years, gradually enriching the gas with heavy elements produced by stellar nucleosynthesis. Each generation of stars forms from slightly more enriched material than the last. The Sun and its planets contain about 2% heavy elements by mass, far more than the ancient stars in globular clusters, which have less than 1%. This enrichment continues today, slowly but steadily, increasing the heavy element content of the interstellar medium. Interstellar medium, the space between stars, is far from empty. In addition to gas, it contains dust, tiny solid particles, typically about a micron across, roughly the size of smoke particles. These dust grains are made of silicates, graphite, and other compounds, with icy mantles in cold regions. Dust makes up only about 1% of the interstellar mass, but it has outsized importance. Dust absorbs and scatters starlight, making distant regions of the galaxy harder to see. The dark lanes visible in images of the Milky Way are dust clouds blocking light from stars beyond. But dust also plays a vital role in star formation. The surfaces of dust, grains, provide sites where atoms can stick together and form molecules. Without dust, molecular hydrogen, necessary for star formation, would be much rarer. Dust also helps cool collapsing gas clouds by radiating away heat as infrared light, allowing the clouds to contract further and eventually form stars. After stars form, radiation pressure from the young stars blows away nearby dust, sometimes creating beautiful shapes like the pillars of creation in the Eagle Nebula. Nebulae come in several varieties, each revealing different aspects of the stellar life cycle. Emission nebulae glow because ultraviolet light from hot, young stars ionizes the surrounding hydrogen gas, causing it to emit visible light. The Orion Nebula is a famous example, visible to the naked eye as a fuzzy patch in Orion's sword. Reflection nebulae appear blue because they reflect light from nearby stars, with blue light scattering more efficiently than red, the same reason Earth's sky is blue. Dark nebulae are dense clouds that block background light, appearing as dark patches against brighter regions. Planetary nebulae, as mentioned earlier, are shells of gas expelled by dying stars, and supernova remnants are expanding clouds of debris from exploded stars, often visible at multiple wavelengths from radio to X-rays. Each type of nebula marks a stage in the cosmic cycle: star formation in emission and dark nebulae, ongoing stellar activity in reflection nebulae, and stellar death in planetary nebulae and supernova remnants. The cycle continues endlessly, matter moving from clouds to stars to remnants and back to clouds again. Stellar winds, steady streams of particles flowing from stars' surfaces, also return material to the interstellar medium. The Sun has a relatively gentle stellar wind, losing about 1/1,000,000th of its mass every 100 million years, a negligible amount over its lifetime. More massive stars have much stronger winds, sometimes losing significant fractions of their mass before they explode as supernovae. Wolf-Rayet stars, extremely hot and luminous, have winds so strong they can strip away the star's entire outer envelope, exposing the bare helium core. These stars lose mass at rates millions of times greater than the Sun. blowing away several Earth masses of material every year. The winds are driven by radiation pressure, with photons transferring momentum to atoms in the star's atmosphere and pushing them outward. In the most extreme cases, stellar winds can be fast enough and dense enough to glow visibly, creating expanding shells of gas around the star. All this mass loss enriches the surrounding space, distributing elements throughout the galaxy. Elements distributed by stars are what make planets and life possible. In the earliest moments after the universe began, only hydrogen, helium, and traces of lithium existed. Everything else, every element heavier than lithium, was created by stars through nuclear fusion or in supernova explosions. Carbon, essential for life, is created when helium nuclei fuse in the cores of red giant stars. Oxygen comes from more massive stars fusing carbon. Silicon, sulfur, calcium, and iron are produced in the late stages of massive star evolution. Gold, silver, platinum, and uranium are created in the explosive environment of supernova or neutron star mergers. Every breath of oxygen you take, every carbon atom in your body, every calcium atom in your bones was created inside a star billions of years ago and returned to space when that star died. The atoms that make up the Earth, the oceans, and every living thing on the planet are all recycled stardust, forged in stellar furnaces and scattered across the galaxy. We are literally made of stars, our existence dependent on the cycles of stellar birth and death that have operated for billions of years. Stars near the Sun provide examples of the variety found across the galaxy. Alpha Centauri, the closest star system, is actually a triple system. Alpha Centauri A and B orbit each other every 80 years, while Proxima Centauri, a dim red dwarf, orbits the pair at a much greater distance. Despite being our closest stellar neighbours at about 4 light-years away, we can't see Proxima with the naked eye because it's so faint. Sirius, the brightest star in the night sky, is actually a binary system consisting of a brilliant white star, Sirius A, orbiting with a white dwarf, Sirius B. The white dwarf is intrinsically faint but interesting because it's one of the nearest white dwarfs, allowing detailed study. Betelgeuse, already mentioned as a red supergiant, is in the late stages of its life and could explode as a supernova any time within the next 100,000 years. When it does, it will briefly appear as bright as the full moon, visible even during daytime, a spectacular event that will be visible to the naked eye for months. Visible events in the sky have always captured human attention. Novae, sudden brightening of stars, were historically mysterious. We now know they occur in binary systems where a white dwarf accretes material from a companion. The accumulated hydrogen on the white dwarf's surface eventually undergoes runaway fusion, causing the star to brighten dramatically for days or weeks before fading back to normal. Supernovae are much brighter and less common, visible even in distant galaxies. Historically, several supernovae were recorded by ancient astronomers as guest stars that appeared suddenly and then faded over months. The Crab Nebula is the remnant of a supernova seen in the year 1054, recorded by Chinese and Arab astronomers. In 1604, a supernova in the Milky Way became the brightest star in the sky for several weeks, bright enough to be seen in her daylight. No supernova has been visible to the naked eye in our galaxy since then, though we've observed many in other galaxies. Astronomers eagerly await the next nearby supernova, which would provide unprecedented detail about these dramatic events. Events like supernovae remind us that the night sky isn't static. Stars move, though their motions are too slow to notice over human lifetimes. The constellations we see today look essentially the same as they did thousands of years ago, but they're slowly changing. Each star has its own motion through the galaxy. Stars near the Sun are all orbiting the galactic center, but at slightly different speeds and on slightly different paths. This results in relative motions, with some stars gradually moving closer to us and others farther away. Over tens of thousands of years, these motions will distort the familiar constellation patterns. The Big Dipper, for instance, will look quite different 50,000 years from now, with some stars having moved significantly from their current positions. In 100,000 years, the constellations will be unrecognizable. The night sky is dynamic on cosmic timescales, with stars following their orbits through the galaxy, their positions slowly evolving in a stately dance that plays out over millennia. Dancing stars sometimes come together in temporary partnerships. When two stars pass close to each other in a dense stellar environment, like a globular cluster, they can interact gravitationally. Sometimes a star passing near a binary system can exchange places with one of the binary members, a process called dynamical exchange. Sometimes two single stars passing close can become gravitationally bound, forming a new binary. These interactions are most common in cluster cores where stellar densities are highest. In the galactic disk where the Sun resides, stars are too far apart for close encounters to be common. The Sun will never experience a close passage with another star during its entire lifetime. The nearest star will always be several light years away, far too distant for any gravitational interaction. Our stellar neighborhood is quiet and stable, with stars maintaining their orbits without interference from neighbors. But in dense clusters, stellar dynamics are much more active, with stars frequently interacting and occasionally colliding. Collisions between stars are rare, but not impossible. When they occur, the results depend on the stars involved. Two main sequence stars colliding would merge into a single more massive star, which would then evolve faster than either original star. A main sequence star colliding with a white dwarf or neutron star can trigger dramatic explosions as material from the normal star is violently heated and compressed. Some types of supernovae might result from white dwarf mergers. Collisions between neutron stars are particularly interesting because they produce gravitational waves and can forge heavy elements through rapid neutron capture. These events are rare, but in a galaxy with hundreds of billions of stars over billions of years, even rare events happen occasionally. Each collision is unique, the outcome determined by the masses, compositions, and orbital parameters of the stars involved. Despite their rarity, stellar collisions contribute to the diversity of objects we observe in the galaxy and play a role in the chemical enrichment of the interstellar medium. Enrichment of heavy elements has gradually increased over the galaxy's history. The oldest stars, formed shortly after the galaxy itself, contain very few heavy elements, sometimes less than 1,000th the amount in the Sun. These ancient stars are called population 2 stars. They formed from gas that had been only lightly enriched by the first generation of massive stars. Younger stars like the Sun, called population 1 stars, contain substantially more heavy elements, about 2% by mass. This increase reflects billions of years of stellar nucleosynthesis and supernova enrichment. The trend continues today. stars forming now will have slightly more heavy elements than the Sun, because the interstellar medium has been further enriched in the 4.5 billion years since the Sun formed. Looking ahead, stars forming billions of years from now will have even higher heavy element content, assuming star formation continues. Eventually, though, star formation will slow as the galaxy's gas supply is exhausted. Most gas will be locked in stars, white dwarfs, neutron stars, and black holes. With little fresh material available, new star formation will gradually cease. Cessation of star formation is far in the future, billions of years away, but inevitable. The galaxy's gas reservoir is finite, and star formation converts gas into stars. Some gas is returned to space by stellar winds and supernovae, but some remains locked in long-lived low-mass stars and stellar remnants. Over time, the balance shifts, with more gas locked away and less available for new stars. The star formation rate in the Milky Way has already declined from its peak billions of years ago. Currently, the galaxy forms about 1 to 3 solar masses of new stars per year, down from perhaps 10 solar masses per year in the past. This decline will continue. Eventually, the galaxy will consist primarily of old, cool stars and stellar remnants, with little or no ongoing star formation. Red dwarfs, with their trillion-year lifetimes, will dominate. White dwarfs will gradually cool and fade. The galaxy will grow dimmer and redder as bright young stars disappear and aren't replaced. This future is certain but distant, giving current stars plenty of time to complete their life cycles. Life cycles of stars operate on timescales that make them essentially eternal from a human perspective. Even short-lived massive stars exist for millions of years, while sun-like stars last billions of years, and red dwarfs will shine for trillions. The processes are so slow that we can never observe a single star complete its evolution. We can only watch many stars at different stages and infer the sequence. It's like looking at a forest and seeing trees of different ages and sizes. You can't watch one tree grow from seed to maturity to death, but you can see saplings, young trees, mature trees, and dead logs, and from those snapshots, understand the life cycle. Similarly with stars, we observe protostars, main sequence stars, giants, supergiants, white dwarfs, neutron stars, and black holes, and from these observations, piece together how one stage leads to the next. The understanding is remarkably complete, confirmed by countless observations and sophisticated computer models that reproduce observed stellar properties with high accuracy. Accuracy of stellar models improves continually as observations become more precise. Modern telescopes can measure stellar properties with extraordinary precision. Astroseismology, the study of stellar oscillations, allows astronomers to probe stellar interiors by analyzing how stars vibrate. Just as earthquakes reveal Earth's internal structure through seismic waves, stellar oscillations reveal stars' internal structure through sound waves traveling through their interiors. Different oscillation modes depend on different internal properties, so by measuring many oscillation frequencies, astronomers can determine a star's core size, internal density profile, and even rotation rate at different depths. The Sun has been studied this way in great detail, confirming our understanding of stellar structure. Many other stars have now been observed with similar techniques, revealing their internal properties and allowing direct tests of theoretical models. These tests consistently show that our understanding of stellar physics is fundamentally correct, though details continue to be refined as observations become more sophisticated. Sophisticated observations extend beyond visible light. Radio telescopes detect emissions from molecules in star-forming clouds and from pulsars. Infrared telescopes peer through dust to see young stars still embedded in their birth clouds. Ultraviolet telescopes observe hot stars and the high-temperature gas in stellar atmospheres. X-ray telescopes detect the hottest phenomena, like gas accreting onto neutron stars and black holes, and the million-degree corona surrounding some stars. Gamma-ray telescopes observe the most energetic events, including supernova and neutron star mergers. By combining observations across the electromagnetic spectrum, astronomers build comprehensive pictures of stellar phenomena that would be impossible to obtain from any single wavelength. Each wavelength provides different information, revealing different aspects of stellar physics. Together, they show stars as complex, dynamic objects with atmospheres, winds, oscillations, magnetic fields, and interior structures, all interacting in ways that determine the star's evolution and ultimate fate. Fate of most stars is to end quietly as white dwarfs, slowly cooling over trillions of years. Only the most massive stars explode as supernovae, and only a fraction of those form neutron stars or black holes. The vast majority, probably 97% or more, will simply shed their outer layers and fade away as white dwarfs. This quiet end is appropriate for objects that have spent billions of years shining steadily, converting hydrogen to helium through patient nuclear fusion. The violence of supernovae, though dramatic and important for enriching the galaxy with heavy elements, is the exception rather than the rule. Most stellar lives are stories of stability and gradual change, not sudden drama. Even the transition from main sequence to giant happens over millions of years, slowly enough that a time-lapse video would be needed to see the change. Stars operate on their own timescales, indifferent to human hurry, following paths determined by physics and their initial conditions. Initial conditions, particularly mass, determine nearly everything about a star's life. More massive stars are hotter, brighter, bluer, and shorter-lived. Less massive stars are cooler, dimmer, redder, and longer-lived. The relationship is predictable and well characterized. Given a star's mass, astronomers can estimate its temperature, luminosity, radius, and lifetime with reasonable accuracy. Other factors matter too. Chemical composition affects opacity, which influences how energy flows through the star. Rotation can affect the star's shape and internal mixing. Magnetic fields can drive stellar winds and create active regions on the surface. But mass is the dominant factor, the single most important property determining how a star will evolve. Two stars with the same mass but slightly different compositions or rotation rates will still follow broadly similar evolutionary paths. Mass determines destiny in stellar evolution, channeling stars into different tracks based on how much material they started with. Material that stars started with came from the interstellar medium, enriched by previous stellar generations. The first stars had only hydrogen and helium, the primordial elements created in the universe's first few minutes. These population 3 stars, as they're called, have never been directly observed because they all died billions of years ago. But we can infer their properties. Without heavy elements, their opacity would be lower, allowing heat to escape more easily. To maintain stable fusion, they likely needed to be more massive than modern stars, perhaps tens or even hundreds of solar masses. Such massive stars would be extremely bright and short-lived, burning through their fuel in just a few million years before exploding as supernovae. These first supernovae created and scattered the first heavy elements, enriching the gas from which the second generation of stars formed. Population 2 stars, including those in globular clusters, formed from this slightly enriched material. Population 1 stars like the Sun formed much later from gas enriched by many cycles of star formation and death. Cycles of stellar generations have operated for most of cosmic history. The first stars formed only a few 100 million years after the universe began, ending the cosmic dark ages and beginning the epoch of reionization. Their ultraviolet light ionized the neutral hydrogen that filled the universe, making it transparent to radiation. Galaxies began to form as gas collected in the gravitational wells created by dark matter. Within those galaxies, stars formed, enriched the gas, and died. New generations of stars formed from the enriched gas. The process repeated, gradually building up the heavy element content of the interstellar medium. The story continues today. Stars are still forming in the Milky Way and other galaxies, continuing the enrichment process. Each new star represents another link in the chain, another generation benefiting from the nuclear alchemy of its predecessors. The universe is gradually converting primordial hydrogen and helium into heavier elements, locking some in stellar remnants, but returning much to the interstellar medium, where it can be incorporated into new stars and planets. Planets benefit directly from stellar enrichment. Rocky planets like Earth couldn't exist without heavy elements. Iron for the core, silicon and oxygen for the rocks, carbon for life, all of these came from stars. Even gas giant planets, though mostly hydrogen and helium, contain heavy elements in their cores and atmospheres. The amount of heavy elements in a star correlates with the likelihood of it having planets. Stars with more heavy elements are more likely to have detected planets, particularly large planets, that are easier to find with current techniques. This makes sense. If the disk of material around a young star contains more heavy elements, there's more solid material available to build planets. The correlation has been well established by exoplanet surveys over the past few decades. It suggests that metal-rich stars, in astronomical terms, where metal means anything heavier than helium, are better candidates for hosting planetary systems. This has implications for where we should search for life, as rocky planets in habitable zones are most likely around stars with substantial heavy element content. Content of heavy elements varies not just among stars, but also throughout the galaxy. The galactic disk has more heavy elements than the halo. The inner regions of the disk have slightly more than the outer regions, reflecting a gradient in star formation activity and enrichment. Stars near the galactic center formed from gas enriched by many earlier stellar generations, in a region with high star formation rates. Stars in the outer disk formed from less enriched material. The Sun, located about halfway out in the disk, has intermediate heavy element content. These variations affect planet formation and potentially the development of life. Regions with very few heavy elements might lack rocky planets entirely. Regions with too many heavy elements might form planets, but have environments dominated by short-lived massive stars and frequent supernovae. Moderate enrichment, like in the solar neighborhood, might be ideal for stable planetary systems with long-lived stars and minimal radiation hazards. We don't know if this is true, but it's an interesting possibility that the Sun's location in the galaxy contributed to Earth's habitability. Habitability of planets depends on many factors, but the stability provided by a long-lived star is certainly important. Stars like the Sun remain on the main sequence for about 10 billion years, providing stable illumination for any orbiting planets. Red dwarfs, though cooler and dimmer, are even more stable, shining steadily for trillions of years with minimal variation. Massive stars, by contrast, live only millions of years, too short for complex life to develop if Earth's history is any guide. Life on Earth took about 3.5 billion years to evolve from simple cells to complex multicellular organisms, and another 500 million years to develop intelligence. This process required a stable star that didn't change significantly over billions of years. Main sequence stars provide this stability naturally. They're in equilibrium, with fusion balancing gravity, maintaining constant temperatures and luminosities for vast stretches of time. This is the environment where life has the best chance to develop, protected by a steady star that faithfully provides energy day after day, year after year, for billions of years, asking nothing in return except to follow the natural laws of physics that govern all stellar evolution. Evolution follows predictable paths, but individual stars can still surprise us. Variable stars change their brightness over time, sometimes regularly, sometimes unpredictably. Cepheid variables pulse with periods ranging from days to months, expanding and contracting, as instabilities in their outer layers drive rhythmic changes. The period of pulsation relates directly to the star's intrinsic luminosity, making Cepheids valuable for measuring cosmic distances. By observing a Cepheid's period, we can calculate how bright it actually is, and by comparing that to how bright it appears, we can determine its distance. This technique has been used to measure distances to nearby galaxies, helping establish the scale of the universe. RR Lyrae variables, similar but fainter, serve as distance markers within our galaxy. Eclipsing binaries vary as one star passes in front of the other from our perspective, blocking its light periodically. Each type of variability reveals something about stellar structure and evolution, turning brightness changes into windows onto stellar physics. Physics governing stellar behavior applies universally, but observing it requires patience and precision. Some variables change over hours, others over months or years. Long-period variables, typically red giants, can vary by factors of hundreds in brightness over cycles lasting months to years. Mira, a famous example, varies from easily visible to the naked eye to invisible over about 11 months. The variations result from pulsations in the star's extended, unstable outer envelope. These old giant stars are nearing the end of their lives, having already exhausted core hydrogen and now burning helium, or in the brief lull between fusion stages. Their outer layers are so loosely bound that they respond dramatically to changes in energy output from deeper within. Eventually, these stars will shed their envelopes entirely, creating planetary nebulae. For now, they pulsate, brightening and dimming in slow rhythms that have been observed and recorded for centuries. Their light curves providing records of stellar behavior over long timescales. Timescales of stellar phenomena span enormous ranges. Some processes happen in fractions of a second. Core collapse during a supernova takes less than a second, yet releases more energy than the Sun will emit over its entire 10 billion year lifetime. Other processes unfold over billions of years. The Sun's evolution from birth to white dwarf will take about 12 billion years total. Red dwarf evolution will take trillions of years. Even within a single star, different regions operate on different timescales. Fusion reactions in the core happen in millionths of a second, but it takes hundreds of thousands of years for the energy to diffuse outward through the radiative zone. Convection in the outer layers turns over in weeks to months. Surface features like sunspots evolve over days to weeks, and the star's overall evolution from one stage to the next takes millions to billions of years. Understanding stars means understanding this hierarchy of timescales and how processes at different speeds interact and influence each other. Interactions between different physical processes create complex stellar behavior. Magnetic fields, generated by motions of charged particles in stellar interiors, can emerge through the surface and create active regions. On the Sun, these appear as sunspots, dark regions where strong magnetic fields suppress convection, making the surface cooler and darker. Sunspots come and go in an 11-year cycle, with periods of many sunspots alternating with periods of few. The cycle reflects changes in the Sun's internal magnetic field, which is generated by the interaction of rotation and convection in a process called a dynastic. Other stars show similar activity cycles, some shorter, some longer than the Sun's. Magnetic activity can accelerate stellar winds, heat outer atmospheres to millions of degrees, and produce flares, sudden releases of energy that brighten the star temporarily. Young stars are especially active, with powerful flares and strong stellar winds. As stars age, their rotation slows and their magnetic activity decreases, eventually settling into quieter middle age. Middle age for Sun-like stars is a period of stability and relative quiet. The Sun is currently about 4.5 billion years old, roughly halfway through its main sequence lifetime. It's slightly brighter now than when it formed, a gradual increase that will continue as the helium ash from fusion accumulates in the core, increasing central density and temperature. But the changes are slow, only about 10% per billion years. Over the next few billion years, the Sun will continue shining steadily, providing Earth with consistent illumination. This stability is common among main sequence stars. Once a star settles onto the main sequence after its formation, it remains there without major changes for most of its life. The equilibrium between gravity and fusion pressure is robust, automatically adjusting to maintain balance. If fusion speeds up, the core heats and expands, which reduces fusion rates back to normal. If fusion slows, the core contracts and heats, increasing fusion rates again. These feedback mechanisms keep main sequence stars stable for billions of years. Stability characterizes most of a star's life, but the transitions between stages can involve rapid changes. When a Sun-like star exhausts core hydrogen and begins climbing the red giant branch, its luminosity can increase by factors of thousands over just a few 100 million years. That's fast by stellar standards, though still glacially slow by human measures. The helium flash, when helium fusion ignites in the core of a low-mass star, happens over just a few seconds, though it occurs deep within the star and doesn't produce any visible sign at the surface. The flash releases enormous energy, but it's absorbed by the outer layers and converted to expansion rather than escaping as light. Similarly, when a massive star's iron core collapses to form a neutron star, the collapse takes less than a second, but the effects, the supernova explosion, unfold over days to weeks as the shock wave propagates outward through the star. Stellar evolution is mostly patient waiting, punctuated by occasional dramatic events, stability interrupted by brief transitions. Transitions between evolutionary stages depend critically on mass. Stars less than about half the Sun's mass will never ignite helium fusion. They'll exhaust their hydrogen, contract, and become helium white dwarfs without ever fusing helium. The universe isn't old enough for any of these stars to have reached that stage yet, since even the smallest red dwarfs take trillions of years to exhaust hydrogen. Stars between about 1/2 and 8 solar masses ignite helium fusion after exhausting core hydrogen, then shed their envelopes and become carbon-oxygen white dwarfs. Stars between roughly 8 and 25 solar masses fuse elements up to oxygen or silicon before their cores collapse, and they explode as supernovae, leaving neutron stars. Stars more massive than about 25 solar masses can fuse elements all the way to iron before collapsing, likely forming black holes. These mass ranges are approximate, with the exact boundaries depending on composition and other factors, but they show how mass channels stars into different evolutionary tracks with different endpoints. Endpoints of stellar evolution are remarkably simple compared to the complexity of living stars. White dwarfs are essentially just carbon and oxygen nuclei surrounded by degenerate electron gas. Neutron stars are mostly neutrons with thin crusts of neutron-rich nuclei. Black holes are pure, gravitational wells described completely by their mass, spin, and electric charge. These remnants have stripped away all the complexity of their parent stars, the layered structure, the ongoing fusion, the atmospheric dynamics, the magnetic activity. What remains is simple, dense, and essentially inert, except for slow cooling or occasional interactions with surrounding material. White dwarfs will cool and fade over trillions of years. Neutron stars will do the same, though they start hotter and have residual magnetic fields that can produce observable effects for millions of years. Black holes will persist essentially unchanged for unimaginable spans of time, slowly evaporating through Hawking radiation over periods vastly longer than the current age of the universe. Age of the universe sets a limit on what we can observe. At about 13.8 billion years old, the universe has existed long enough for multiple generations of stars to form, live, and die. The most massive stars have cycled through many generations, each generation enriching the interstellar medium. Sun-like stars have had time to complete one full lifetime if they formed early. Red dwarfs that formed at the beginning are still on the main sequence and will remain there for trillions more years. We're living in a young universe, cosmically speaking, with most stars still ahead of us in time rather than behind. The universe will continue forming stars for billions of years, though the rate will gradually decline as gas supplies diminish. Eventually, star formation will cease, and the universe will be populated only by stellar remnants and the longest-lived red dwarfs. But that's so far in the future that it bears little relevance to the current stellar population, which is still vibrant and actively forming new stars. New stars continue forming in molecular clouds throughout the galaxy. The Orion Nebula, visible to the naked eye, is one of the nearest star-forming regions, at about 1,300 light-years away. It contains thousands of young stars, many still surrounded by disks of material from which planets may form. The nebula glows because ultraviolet light from hot young stars ionizes the surrounding hydrogen. Other star-forming regions are visible across the sky, some bright and nearby, others distant and obscured by dust. Each region tells the same basic story. A molecular cloud becomes unstable and begins to collapse. Fragmentation creates many collapsing cores rather than one giant star. Each core forms a star or a multiple star system. The stars ignite, blow away remaining gas with their radiation and winds, and eventually disperse as they orbit the galaxy. The process has operated for billions of years and will continue for billions more, steadily converting gas into stars and enriching the interstellar medium with the products of stellar nucleosynthesis. Nucleosynthesis in stars follows well-understood fusion pathways. Hydrogen fuses to helium through the proton-proton chain in stars like the Sun, or the CNO cycle in more massive stars. Helium fuses to carbon and oxygen through the triple alpha process. Carbon, neon, oxygen, and silicon burning follow in massive stars, each stage producing progressively heavier elements. The fusion reactions release energy because the products are more tightly bound than the reactants. Iron represents the end of this line. Fusing iron absorbs energy rather than releasing it, so iron doesn't serve as fuel. Elements heavier than iron are created through neutron capture, either slowly during a star's life or rapidly during supernova explosions and neutron star mergers. These processes have been studied in detail, both theoretically and through observations of stellar spectra and supernova ejecta. The agreement between theory and observation confirms our understanding of how stars create elements and validates the stellar nucleosynthesis theory. Theory and observation work together to advance stellar astrophysics. Theory predicts how stars should behave based on physical laws. Observations test those predictions. When theory and observation agree, we gain confidence in our understanding. When they disagree, we refine the theory or look for observational errors. This cycle has operated for over a century, gradually building a comprehensive picture of stellar structure and evolution. Early theories assumed stars were primarily hydrogen, which turned out to be correct. Observations of stellar spectra confirmed the presence of hydrogen and helium. Theories of nuclear fusion, developed in the 1930s and 40s, explained how stars generate energy. Observations of stellar evolution in clusters confirmed theoretical predictions of how stars evolve. Computer models developed from the 1960s onward allowed detailed calculations of stellar interiors. Modern observations from space-based and ground-based telescopes continue to refine our understanding, revealing subtle effects and testing predictions in ever more detail. Detail in modern observations is extraordinary. Interferometry, combining light from multiple telescopes, can resolve features on stellar surfaces. We've measured the diameters of giant stars, seen star spots on other stars, and mapped the surfaces of nearby supergiants. Spectroscopy reveals the chemical compositions of stellar atmospheres with remarkable precision, detecting elements present in quantities of only a few parts per million. Astroseismology probes stellar interiors through oscillation modes. gravitational wave detectors observe the final moments of neutron star and black hole mergers. X-ray and gamma-ray satellites detect the highest energy phenomena. Radio telescopes observe molecular clouds and pulsar emissions. Each technique provides complementary information, building a multifaceted picture of stars at different stages of evolution and in different environments. The combination of techniques allows astronomers to study stars with a level of detail that would have been unimaginable just decades ago. Decades of progress have revolutionized our understanding, but fundamental questions remain. We don't fully understand the mechanisms of supernova explosions. Computer simulations can reproduce many observational features, but the details of how the shockwave successfully ejects the star's outer layers remain incompletely understood. The formation of planets around stars is well understood in broad outline, but poorly understood in detail. We don't know why some stars have planets and others don't, beyond the correlation with metallicity. The exact role of magnetic fields in star formation and stellar evolution is still being worked out. The nature of dark matter, which dominates the gravity-holding galaxies together, remains mysterious. These unknowns don't undermine our general understanding of stars. The broad picture is solid, confirmed by countless observations. But they remind us that science is an ongoing process, with each answer generating new questions, each discovery revealing new phenomena to investigate. Investigation of stellar phenomena continues across many fronts. Exoplanet surveys are discovering thousands of planets and beginning to characterize their atmospheres. Gravitational wave detectors are observing dozens of mergers per year, revealing the population of stellar mass black holes and neutron stars. Time domain astronomy, continuously monitoring the sky for transient events, is discovering supernovae, stellar flares, and other variable phenomena in real time. Surveys mapping the positions and motions of millions of stars are revealing the structure and history of the galaxy. Spectroscopic surveys are measuring the chemical compositions of hundreds of thousands of stars, tracing the enrichment history of different galactic regions. Each of these programs generates enormous datasets requiring sophisticated analysis. Machine learning and artificial intelligence are increasingly used to find patterns and classify objects in these vast datasets. The pace of discovery continues to accelerate, with new telescopes and new techniques constantly expanding our knowledge of stars. Knowledge of stars shapes our understanding of the universe as a whole. Stars are the primary visible components of galaxies. They produce most of the light we observe from distant galaxies. Their deaths enrich the interstellar medium, enabling planet formation and life. Their evolution is tied to cosmic history, with the first stars forming just a few 100 million years after the beginning, and the last stars destined to shine trillions of years in the future. Understanding stars means understanding how galaxies evolve, how elements are created, how planets form, and how the universe changes over time. Stars are not isolated objects. They're integrated into the cosmic ecosystem, shaped by their environment and shaping it in return. The gas from which they form was enriched by previous stellar generations. The elements they create will be incorporated into future generations. This cycle of matter through stars and back to the interstellar medium is one of the fundamental processes driving cosmic evolution. Cosmic evolution is written in the light we observe. Distant galaxies show us what the universe looked like billions of years ago. Their stars are younger, their chemical compositions different, their formation rates higher. Nearby galaxies and stars in the Milky Way show us the present-day universe, enriched by billions of years of stellar processing. By comparing populations at different distances and ages, we trace how the universe has changed. Early galaxies were smaller, bluer, and more irregular. Modern galaxies are larger, redder, and more structured. The star formation rate in the universe peaked about 10 billion years ago and has been declining since. These trends emerge from observations of thousands of galaxies at different distances. Each galaxy contributes one data point, and together they tell the story of cosmic history. Stars, as the visible components of galaxies and the agents of chemical enrichment, are central to this story. Their collective evolution determines how galaxies change over time. Time plays a dual role in astronomy, as both the medium of evolution and the dimension we observe across. When we look at a star 1,000 light-years away, we see it as it was 1,000 years ago. Look at a galaxy 1 million light-years distant, and we see it as it was 1 million years ago. The farther we look, the farther back in time we see. This makes astronomy unique among sciences. We can directly observe the past, not by inference or reconstruction, but by simply looking far enough away. The light reaching us now has been traveling through space for millions or billions of years, carrying information about the objects as they were when the light left them. This allows us to study cosmic evolution directly rather than just theoretically. We can see young stars and compare them to old stars. We can see early galaxies and compare them to modern galaxies. The universe provides its own fossil record, written in light, available to anyone with a telescope sensitive enough to detect it. Sensitivity of modern telescopes exceeds what early astronomers could have imagined. The largest telescopes can detect objects billions of times fainter than what the human eye can see. They can observe wavelengths invisible to us, from radio to gamma rays. They can track objects moving across the sky or changing in brightness. They can split light into detailed spectra, revealing chemical compositions. They can combine light from multiple telescopes to achieve resolution equivalent to telescopes kilometers across. And they can do all this automatically, observing continuously and generating datasets too large for humans to examine individually. Automated pipelines process the data, identify interesting objects, and alert astronomers to transient events. This combination of technology and automation has transformed astronomy from a field limited by what could be observed in a single night to one limited only by the collective telescope time available and the computational resources to process the results. Results from modern surveys have confirmed many theoretical predictions, while revealing surprises. We predicted that planets should be common, and they are, with most stars hosting at least one planet. We predicted that stellar populations should show chemical enrichment over time, and they do, with younger stars containing more heavy elements. We predicted that the universe should contain many stellar remnants, white dwarfs, neutron stars, and black holes, and observations have found large populations of each. But we've also been surprised. Exoplanets come in configurations we didn't expect, including hot Jupiters orbiting extremely close to their stars and super-Earths with no analogue in our solar system. Neutron star mergers produce heavier elements through rapid neutron capture more efficiently than we thought. Some stellar phenomena, like fast radio bursts, were completely unexpected discoveries with no theoretical prediction beforehand. The universe is both predictable, following known physical laws, and surprising, exhibiting phenomena we haven't yet imagined. Imagination plays a role in science, but it must be grounded in observation and theory. Scientists propose hypotheses, explanations for observed phenomena, or predictions of unobserved effects. These hypotheses are tested through observation and experiment. Those that survive testing become accepted theories. Those that fail are discarded or modified. This process requires creativity to imagine possible explanations and rigor to test them properly. In stellar astrophysics, many phenomena were predicted theoretically before being observed. White dwarfs were predicted before they were definitively identified. Neutron stars were predicted decades before pulsars revealed their existence. Black holes were predicted based on general relativity long before observational evidence accumulated. In each case, the theoretical prediction gave observers something specific to look for, focusing the search. But observation also reveals phenomena that weren't predicted, expanding the scope of what theories must explain. The interplay between theory and observation drives progress. Progress in understanding stars has been steady and cumulative. Each generation builds on previous work, adding observations, refining theories, and expanding the scope of what we can explain. Early astronomers catalogued stars and noted their positions. Later generations measured their brightnesses and spectra. Still later, theoretical work explained stellar energy generation through fusion. Modern researchers probe stellar interiors, observe exoplanets, and simulate stellar evolution on supercomputers. At each stage, the fundamental understanding remained valid even as details were added and refined. We didn't abandon earlier knowledge as we learned more. We built upon it, extending and deepening our understanding. This cumulative nature of scientific knowledge gives confidence that our current understanding, while incomplete, is fundamentally correct. Future discoveries will add detail and perhaps revolutionize some areas. But the core picture of stellar structure and evolution is solid, tested against countless observations. Observations span not just different wavelengths, but different time domains. Some phenomena unfold slowly, like the evolution of a star over millions of years. Others happen rapidly, like the collapse of a stellar core in less than a second. To observe both, we need different strategies. Long-term monitoring programs track stars over years or decades, watching for gradual changes or periodic variations. Time domain surveys observe the same regions of sky repeatedly, looking for transient events like supernova, flares, or asteroids. Some transients require rapid response, with alerts sent out so that other telescopes can follow up within hours. Others develop slowly enough that observations can be planned in advance. The diversity of timescales in stellar phenomena requires diverse observing strategies. Some important questions can only be answered by patient monitoring over long periods. Others require catching rare events as they happen. Together, these approaches build a comprehensive picture of stellar behavior across all timescales. Comprehensive pictures emerge from combining many observations. Any single observation provides limited information. A spectrum tells us about a star's temperature and composition, but not its size or distance. A measurement of brightness tells us how much light reaches Earth, but not how much the star emits intrinsically. Combining multiple observations allows us to determine more properties, measure both brightness and spectrum, and we can estimate distance. Observe binary stars orbiting each other, and we can measure their masses. Watch planets transit across a star's face, and we can determine the star's size. Each additional observation adds constraints, narrowing the range of possible stellar properties until we can determine masses, sizes, temperatures, luminosities, ages, and compositions with reasonable accuracy. For nearby stars, we can achieve impressive precision. For distant stars, we have less information, but even limited data can reveal basic properties. The key is using multiple techniques that provide complementary information. Information about stars is encoded in their light. Brightness tells us about luminosity and distance. Color tells us about temperature. Spectra tell us about composition, surface gravity, magnetic fields, and rotation. Variability tells us about pulsations, eclipses, or other dynamic processes. Polarization tells us about magnetic fields and scattering. The Doppler shift tells us about radial velocity and can reveal unseen companions. All of this information travels to us at the speed of light, crossing vast distances without degradation, except for dimming according to the inverse square law. Light is the messenger, carrying information from stars to our telescopes, where we decode it and learn about objects we'll never visit. The fact that we can learn so much from light alone is remarkable. We can determine what stars are made of, how hot they are, how massive, how old, and what stage of evolution they've reached. We can even detect planets orbiting them and characterize those planets' properties. All from light. Light from the sun takes about 8 minutes to reach Earth, making the sun the star we can study in greatest detail. We can resolve features on its surface, track sunspots and solar flares, measure oscillations that probe the interior, and study the solar wind flowing past Earth. The sun serves as a laboratory for stellar physics, where processes that occur in all stars can be observed with unparalleled clarity. Techniques developed for solar observations are often extended to other stars. Helioseismology, the study of solar oscillations, led to asteroseismology for other stars. Observations of the solar corona informed models of stellar corona. Studies of the solar magnetic cycle guide understanding of magnetic activity in other stars. The sun is both an object of study in its own right and a reference point for understanding stars more generally. It's a typical star in many ways, making it a good representative of the broader stellar population, yet close enough to observe in detail that we can test theories rigorously. Theories of stellar structure rest on a few fundamental principles. Hydrostatic equilibrium, the balance between pressure and gravity, determines how density and pressure vary with depth. Energy transport, whether by radiation, convection, or conduction, determines how energy flows from core to surface. Energy generation through fusion determines how much energy is available. Mass conservation ensures that the total mass equals the sum of mass at all depths. These principles, encoded as differential equations, can be solved numerically to predict stellar structure. The solutions depend on initial conditions, primarily mass and composition, and evolve as the star ages and its composition changes due to fusion. The equations have been solved for stars of many different masses and compositions, building a library of stellar models that can be compared to observations. The agreement between models and observations validates the underlying physics and gives confidence that we understand how stars work. Understanding how stars work has practical applications beyond pure science. Cepheid variables serve as distance indicators, allowing us to measure distances to nearby galaxies and calibrate the cosmic distance ladder. White dwarfs of a particular type, called type Ia supernovae, serve as standard candles for measuring very large distances, which led to the discovery of cosmic acceleration. Stellar ages help date galactic structures and events. Stellar nucleosynthesis explains the origin of elements, relevant to everything from geology to biology. Understanding solar activity helps predict space weather that can affect satellites and power grids. While these applications weren't the motivation for studying stars, they demonstrate that fundamental research often produces unexpected benefits. Understanding the universe advances human knowledge and occasionally proves useful in practical ways. But even without applications, the knowledge is valuable in itself, satisfying curiosity and expanding our understanding of nature. Nature's patterns often reveal deeper principles. The main sequence in the Hertzsprung-Russell diagram isn't arbitrary. It represents stars in equilibrium, burning hydrogen in their cores. The fact that most stars lie on the main sequence shows that this phase dominates stellar lifetimes. Giants and supergiants, though prominent, are rare because stars spend relatively little time in those stages. White dwarfs are common because they're the end state of most stars, but they're faint and easy to miss in surveys. These patterns reflect the underlying physics of stellar evolution. Similarly, the mass-luminosity relationship, where more massive stars are more luminous, follows from how fusion rates depend on temperature and density. The period luminosity relationship for Cepheids emerges from how pulsations depend on stellar radius and mass. These patterns aren't coincidences. They're manifestations of physical laws operating in stellar environments. Recognizing patterns helps us understand those laws and apply them to predict stellar behavior. Behavior of stars can be predicted with confidence for the next few billion years. The Sun will remain on the main sequence for about 5 billion more years, gradually brightening but otherwise stable. Red dwarfs will continue shining steadily for trillions of years. White dwarfs will cool slowly, persisting as embers for even longer. Massive stars will continue forming, living briefly, and exploding as supernovae. The overall stellar population will gradually age as the star formation rate declines. These predictions rest on well-tested physics and have high confidence. We're less certain about details far in the future, like exactly when the last star will form, or how quickly galaxy mergers will redistribute stellar populations. But the broad outlines are clear. Stars will continue to operate as they have for billions of years, following the same physical laws, evolving through the same stages, and producing the same outcomes. The universe's stellar epoch is far from over. Over the next billions of years, the stellar content of the universe will change gradually but dramatically. Currently, the soothe universe is in its prime, with vigorous star formation and a mix of stars at different evolutionary stages. Billions of years from now, star formation will have slowed considerably. The gas supply will be depleted, with much of it locked in stars or stellar remnants. The remaining gas will be increasingly metal-rich, enriched by countless stellar generations. New stars forming from this enriched material will have higher metallicity than current stars, but new stars will be rare. The stellar population will be dominated by old stars, primarily red dwarfs still on the main sequence, along with white dwarfs, neutron stars, and black holes from earlier generations. The universe will be dimmer and redder, with the bright blue stars that characterize young stellar populations absent. This transition will happen gradually, with no sharp boundary, as the star formation rate slowly declines from its current level to near zero. Zero star formation might eventually be reached, but where? Uncertain exactly when. Some gas will always be present, returned by stellar winds and supernovae. But whether this gas can cool and collapse to form new stars depends on many factors, including the density of the intergalactic medium and the continuing expansion of the universe. In some models, star formation continues at a low level for trillions of years. In others, it effectively ceases much sooner. Either way, the era of abundant star formation will end. The universe will enter a new phase dominated by stellar remnants and the longest-lived stars. This future might seem melancholy, but it's simply the natural consequence of the processes we observe today, extrapolated forward. Stars convert gas into heavier elements and stellar remnants. Eventually, most gas becomes bound in long-lived objects. Star formation slows. The cycle continues at a lower rate until it becomes negligible. The universe transforms from bright and active to dim and quiescent. Quiescent doesn't mean dead. White dwarfs will still glow, cooling gradually. Neutron stars will still exist, rotating and occasionally flaring if they accrete material. Black holes will persist, patient and unchanging. Red dwarfs will still shine, their dim light the last stellar illumination in a darkening cosmos. These remnants and long-lived stars will orbit in galaxies, maintaining the structures built up over billions of years of star formation. Galaxies themselves will continue to exist, though they'll merge over time as cosmic expansion slows locally and gravity pulls them together. The end result, trillions of years from now, will be a universe of galaxy-sized elliptical galaxies, filled with cooling remnants and the last flickering red dwarfs. It sounds bleak, but it's also peaceful. The violent phases, supernovae, stellar collisions, intense star formation will be over. What remains will be stable and quiet, slowly cooling toward equilibrium. Equilibrium, in thermodynamics, is the state of maximum entropy where no more changes occur. The universe is currently far from equilibrium. Energy flows from hot stars to cold space. Gravitationally bound structures, like galaxies, exist despite the overall expansion. Stars create order locally by fusing elements and organizing energy flows. Eventually, thermodynamics suggests the universe will reach equilibrium. All stars will have died or faded. All black holes will have evaporated. Matter will be spread thinly, no longer concentrated in galaxies. The temperature will be uniform, near absolute zero. This heat death of the universe is far in the future, perhaps 10 to the 100 years or more, a timescale that makes the current age of the universe seem like an eye blink. We're living in the universe's youth, when energy gradients exist and complex structures form. The stars we see are part of this out of equilibrium phase, temporary structures that arise because the universe hasn't yet settled into its final state. Final states depend on initial conditions, and the universe's initial conditions were set in its first moments. The density of matter, the expansion rate, the tiny fluctuations that grew into galaxies, all were determined early on. Those conditions allowed stars to form and evolve as they have. Different initial conditions would have produced a different universe, perhaps one where stars couldn't form, or where they all formed and died quickly. We live in a universe where conditions permit long-lived stars, stable stellar evolution, and the gradual enrichment of heavy elements. Whether these conditions are typical among possible universes or special in some way is unknown. We can only observe our own universe, but within it, the parameters seem well tuned for rich stellar populations and long timescales for evolution. This allows complexity to develop, planets to form, and perhaps life to arise. Stars are central to this story, being the sources of energy and elements that make complexity possible. Possibility of life depends on stars in multiple ways. Stars provide energy through their light. This energy powers photosynthesis on Earth, and presumably could power other metabolisms on other planets. Stars also produce the heavy elements necessary for rocky planets and complex chemistry. Carbon-based life requires carbon, oxygen, nitrogen, and other elements forged in stars. Even the stability required for life to evolve over billions of years depends on stars, specifically long-lived main sequence stars that provide consistent illumination. Without stars, the universe would be dark, cold, and composed only of hydrogen and helium. No planets, no chemistry beyond the simplest molecules, no energy sources for life. Stars transform the universe from a simple collection of light elements into a rich environment where complexity can develop. They're engines of transformation, taking simple inputs and producing complex outputs, creating conditions where the universe becomes interesting. Interesting phenomena often emerge from simple rules. Stars follow straightforward physical laws: gravity, thermodynamics, nuclear physics. Yet, from these simple rules emerges the rich diversity of stellar types and evolutionary paths. The same basic principles produce red dwarfs that shine for trillions of years, and blue supergiants that explode after a few million. They produce stable main sequence stars and variable stars that pulsate regularly. They produce white dwarfs, neutron stars, and black holes. The diversity emerges from different initial masses and compositions, playing out under the same physical laws. This is characteristic of complex systems. Simple rules can produce intricate behavior when the system has many components and non-linear interactions. Stars are complex systems, with gravity competing against pressure, energy generation coupled to temperature, and composition evolving through fusion. The result is behavior that's predictable in outline, but rich in detail. Detail matters when studying individual stars, but broad patterns matter when studying stellar populations. Individual stars have quirks, rotation rates, magnetic fields, companions that affect their evolution in small ways. But statistically, stars of similar mass and composition follow similar paths. This allows us to make predictions about groups of stars, even if we can't predict every detail about individuals. We can calculate the average lifetime of stars with the Sun's mass, even if the exact lifetime of the Sun depends on details we don't know precisely. We can predict how many stars in a cluster will have become red giants after a given time, even if we can't predict exactly which stars. This statistical approach is powerful because it averages over the unpredictable details and reveals the underlying trends. It's how we study stellar populations in distant galaxies, where we can't observe individual stars, but can measure average properties, like color and luminosity, that tell us about the population's age and composition. Composition of stellar populations varies with location in galaxies. Galactic centers have higher metallicity than outer regions. Spiral arms have more young stars than the space between arms. Globular clusters have different populations than the galactic disk. These variations reflect differences in star formation history and enrichment. Regions with vigorous star formation over long periods have experienced more enrichment. Regions where star formation was brief or ended long ago have less enrichment. By mapping these variations, we reconstruct the galaxy's history, determining when and where stars formed and how material cycled between stars and the interstellar medium. The Milky Way shows evidence of past merger events visible in the kinematics and compositions of stellar streams. Other galaxies show different patterns reflecting their unique histories. Each galaxy is an archive of its own past, written in the properties of its stellar populations. Populations of stars in globular clusters are particularly interesting. These clusters, formed early, contain hundreds of thousands to millions of stars, and have survived for over 10 billion years. Their stars are metal poor, reflecting formation from gas only lightly enriched by the first stellar generations. Many globular clusters show evidence of multiple stellar populations with slightly different ages and compositions, suggesting complex formation histories. The clusters orbit in galactic halos, following eccentric paths that carry them through the galactic disk periodically. Some may have originally been the cores of dwarf galaxies that merged with the Milky Way. Their stars are old, many nearing the end of their main sequence lifetimes, with evolved stars visible as red giants. Studying globular clusters provides insights into the early universe and tests theories of stellar evolution for old, low metallicity stars. Testing theories requires comparing predictions to observations. For stellar evolution, one key test is comparing theoretical isochrones, curves showing where stars of the same age fall in the Hertzsprung-Russell diagram, to observations of star clusters. Clusters provide ideal test cases because their stars all formed at the same time from the same gas cloud. They should all lie along a single isochrone corresponding to the cluster's age. Observations generally agree well with theoretical isochrones, confirming that stellar evolution models are accurate. Small discrepancies reveal areas where models need refinement, perhaps in how convection is treated or how mass loss proceeds. These refinements improve the models, which can then be tested against new observations. This cycle of prediction, observation, comparison, and refinement is how science progresses, gradually building more accurate and comprehensive theories. Theories become more reliable as they're tested and refined, but they're never final. Science doesn't prove things true in an absolute sense. It builds models that explain observations and make testable predictions. When predictions match observations, we gain confidence in the model. When they don't, we revise the model. Models that survive extensive testing become well-established theories we trust for making predictions. But there's always the possibility that new observations will reveal limitations or exceptions. This provisional nature of scientific knowledge isn't a weakness, it's a strength, keeping us open to new evidence and new ideas. In stellar astrophysics, the core models of stellar structure and evolution are very well established, tested against countless observations, but details continue to be refined, and new phenomena occasionally surprise us. The field remains active and vibrant, with discoveries still being made, and questions still being answered. Questions about stars span from the specific to the profound. How exactly do massive stars explode as supernovae? What determines whether a collapse produces a neutron star or a black hole? How common are planets in the habitable zones of other stars? Are there other stellar phenomena we haven't yet discovered? These are specific questions addressable through observation and theory. But stars also raise broader questions. Why do the laws of physics have the form they do? Why is the universe structured to allow stable stars and complex chemistry? Is life common wherever conditions permit, or are we unique? These profound questions touch on physics, chemistry, biology, and philosophy. They remind us that studying stars isn't just about understanding distant balls of gas. It's about understanding our place in the universe, the processes that created the elements in our bodies, and the conditions necessary for existence. Stars connect us to the cosmos. Cosmic connections are more than metaphorical. Every atom in your body, except hydrogen, was created in stars. The oxygen you breathe, the carbon in your cells, the calcium in your bones, the iron in your blood, all were forged in stellar interiors through nuclear fusion or created in supernova explosions. After those stars died, the atoms were scattered into space, mixed with the interstellar medium, and eventually incorporated into the molecular cloud that collapsed to form the sun and planets. Earth formed from this stardust, and life arose from the chemical elements available. We are literally made of stars, our bodies assembled from atoms, with histories spanning billions of years and countless light years. This isn't poetry, it's physics and chemistry, the natural consequence of stellar nucleosynthesis and cosmic recycling. Every element heavier than helium in the universe was created by stars. We're products of that process. Processes operating in stars follow physical laws that apply throughout the universe. Gravity, thermodynamics, nuclear physics. These laws work the same way everywhere. A star 10,000 light years away follows the same rules as one in our neighborhood. A galaxy 10 billion light years away, seen as it was 10 billion years ago, contains stars operating according to the same physics. This universality is remarkable and not logically necessary. We might have found that distant regions of the universe operate differently. But every observation confirms that physical laws are universal. Light from distant galaxies shows the same spectral lines as light from nearby stars, indicating that atoms behave identically everywhere. Gravitational interactions in distant galaxy clusters follow the same rules as interactions in our local group. The universe is coherent, governed by consistent laws that don't vary with location or time. This makes the universe comprehensible and allows us to extrapolate from local observations to cosmic conclusions. Conclusions drawn from stellar observations inform our understanding of the universe's past and future. By studying how stars evolve, we understand how galaxies change over time. By measuring stellar ages, we constrain the age of the universe. By observing stellar populations at different distances, we see cosmic history unfold. By understanding stellar nucleosynthesis, we explain the origin of elements. Stars are tools for cosmology, probes of the universe's structure and evolution. But they're also objects of intrinsic interest, worthy of study for their own sake. Each star is a world unto itself, a ball of plasma held together by gravity, powered by fusion, slowly evolving over timescales that dwarf human history. Understanding stars means understanding some of the most fundamental processes in nature: how matter behaves under extreme conditions, how energy is generated and transported, how structures arise from gravity. Gravity is the fundamental force that creates stars. Without gravity, gas clouds wouldn't collapse, stars wouldn't form, the universe would remain forever, a thin, expanding mix of gas with no structure. Gravity enables stars to exist, and stars enable everything else. They produce light, create heavy elements, and provide stable energy sources for planets. The universe's complexity rests on gravity's ability to pull matter together against the dispersing effect of expansion. This is possible because early density fluctuations gave gravity something to work with, slightly denser regions that could grow over time. Without those initial fluctuations, imprinted in the cosmic microwave background, gravity would have nothing to amplify. With them, gravity creates structure on all scales, from stars to galaxies to superclusters. Stars are intermediate scale structures, larger than planets but smaller than galaxies, sitting at a sweet spot where gravity can compress matter enough to ignite fusion, without creating objects so massive they collapse immediately to black holes. Black holes, white dwarfs, and neutron stars represent the endpoints of stellar evolution, but they're not separate from the story of stars. They're what remains after stars complete their life cycles. Each type represents a different balance between degeneracy pressure and gravity. White dwarfs are supported by electron degeneracy pressure. Neutron stars are supported by neutron degeneracy pressure. Black holes have no pressure that can resist gravity at all, collapsing to singularities. These remnants carry forward the legacy of their parent stars, containing the processed material created by billions of years of fusion. White dwarfs are mostly carbon and oxygen. Neutron stars are mostly neutrons, with exotic matter in their cores. Black holes contain whatever matter fell in, now crushed beyond recognition. But in all cases, the material originated in the stars was transformed by stellar processes and now exists in these extreme final states. Understanding stellar remnants completes the picture of stellar evolution. Pictures of stellar evolution reveal a cosmic cycle operating on the grandest scales. Gas clouds collapse to form stars. Stars fuse light elements into heavy ones. Stars die, returning processed material to space. New stars form from the enriched material. The cycle repeats, each iteration enriching the gas further. Over billions of years, the universe transforms from simple to complex, from pure hydrogen and helium to a mixture including all 90-something naturally occurring elements. This enrichment enables planets, chemistry, and life. Without it, the universe would remain forever simple, unable to generate complexity. Stars are the engines driving this transformation, taking simple inputs and producing complex outputs, creating the conditions necessary for the universe to become interesting. Their patient work over billions of years has built the world we inhabit. Inhabiting a universe filled with stars, we're privileged to observe and understand them. From our small planet orbiting an ordinary star, we can look out and see billions of other stars, each with its own story. We can measure their properties, predict their futures, and trace their histories. We can understand the processes that power them and the cycles that connect them. We're made of the same elements created in their cores, breathing the oxygen they produced, built from the carbon they forged. The light from stars that died before Earth formed travels through space and reaches our telescopes, carrying information across billions of years. Every photon tells a story. Every spectrum reveals composition and temperature. Every observation adds to our understanding. Stars are distant, but they're not alien. They operate according to laws we can understand, following patterns we can predict. They're part of the same universe we inhabit, governed by the same physics, connected to us through the elements they create and the light they emit. Understanding stars means understanding our origins and our place in the cosmos. So wherever you are, allow your mind to rest now. Let your breath slow like the cooling of an ancient star. Let your thoughts grow soft and distant, like starlight that's traveled for thousands of years before reaching your eyes. The stars will continue their patient work tonight and every night. They'll burn their hydrogen steadily, following the same nuclear pathways they've followed for billions of years. They'll shine through the darkness, their light spreading outward in all directions, most of it traveling through empty space to destinations unknown. Some of it will reach Earth, as it always has, as it always will, for as long as stars shine and eyes exist to see them. The journey through stellar lives doesn't end. It simply pauses here, in this quiet moment, as you settle into rest. Tomorrow, the sun will rise again, the same sun that's risen every day for 4.5 billion years. The same sun that will continue rising for 5 billion more. The same ancient processes that birthed our sun continue birthing new stars in distant clouds. The same patient fusion that powers our daylight powers countless other worlds, orbiting countless other suns. You're connected to all of it through the atoms in your body, each one carrying a history that spans stars and eons. For now, though, let the stars carry on without your attention. They know their paths. They follow their rhythms. Rest well, and thank you for wandering among the stars with us tonight.